11.2, using iteration to find an approximation for the root of the equation f of x equals 0. This is the second video for chapter 11 of the pure notes for A2. So we're going to start off with trial and improvement. As I mentioned in the last video, this is the topic from GCSE that this part of the course links to. So the easiest way to go about doing this is on your calculator. So if we go to number 9, table, and then it says f of x, what we're going to do, just like we did previously, is let f of x equal the function in the question. So I'm going to put that into the calculator using the x button at the top to be the variable. Press equals, it then says g of x. We are not interested in the second function, so just press equals again, and I'm going to take my range from 0 to 10, stepping in ones, and what we are looking for is that change of sign in f of x. So f of 1 is equal to -2, f of 2 is equal to 5. So just like you should have seen at GCSE, we can make a note of that. Oh, heck. Let's just erase that bit. So we've got -2 and 5. And then I want to comment on whether it's too low or too high. So obviously -2 is low, 5 is high. So what we're doing here is looking for that change of sign because we've got it equal to 0. We could have put a 5 at this side and then we'd be looking for it being a little bit above 5 and a little bit below 5. So if we did 2x squared plus x is equal to 5. The problem with that then is it makes your conclusions a little bit harder to deal with. So what we're going to do is, this is given as an interval, so we know that the root is in the interval 1 to 2. I'm going to go again, so I don't need to enter it again, just press equals. So I'm going to start at 1, finish at 2, and this time my step is going 0.1. And scrolling down, I'm looking for a change of sign, so 1.3 to 1.4 is where my change of sign is happening. So I've got -0.32 and 0.32. That one's too low, that one's too high. So what we've got here is the root is in the interval 1.3 to 1.4. Let's go for one more. So I can start at 1.3 to 1.4. My range, well, my step is getting smaller every time because obviously I'm reducing. You can generally only go up to 10 in terms of your table. You might want to pause the video just to make sure you can use your calculator. You should have come across using this. Finding domain and range is quite useful for that as well. So 1.35, we've got -5 times 10 to the -3. That's a 0 at the beginning, and then I've got 0.0592. So that one's too low, that one's too high. And what that is telling us is that our root is going to be 1.4 to 1 decimal place, because we know that we are lying in the interval 1.35, 1.36, and that everything that lies between those two numbers would round to 1.4 to 1 decimal place. So by going that one step further, so taking it to 0.01, I've found my answer to 0.1, to an accuracy of 0.1, and that we're going to be using that when we're asked to prove values later in the examples. So what we're going to do is look at what's called the iterative method. And again, you've seen iteration before in terms of sequences. And so the idea is that we just keep substituting numbers in to get closer and closer to the value that I'm looking for. So I've turned my calculator back on to calculation, so number 1. I'm going to talk about these 3 graphs after we've done this first example, so we will come back to the graphs. They are really important, and we have seen exam questions already where this topic has been focused on the graph rather than on the written method. So it is important that you understand where those graphs have come from, but I think it makes sense to do it following this example. So the first thing we're going to do is we're looking at the formula 2x squared plus x minus 5, and in an iterative formula we rearrange it to be x equals g of x. I'm going to scribble that out because that's wrong. There's more than 2 answers. So just pause the video and take a moment to rearrange it so that you get x equals. There's a number of different ways that you can do it. Okay, so I might make that x the subject there. So that would be x is equal to 5 minus 2x squared. We could make an x out of here the subject. So if I take the 5 and the x across to the other side, so I've added that, subtracted that, divided by 2. So that's equal to x squared. Therefore, I need to square root it. And I'm going to go for the positive square root here. Another way that we could do it is if we factorise the x out. So I'll do this one into 2 steps. So we've got 2x plus 1 is equal to 5. So I have taken the 5 across, factorised out an x. So that gives me x is equal to 5 over 2x plus 1. And finally, we could go for this again, but instead of going for the square root, I could divide it by 2x. So I've got 5 minus x, take those 2 to the other side, and then divide by 2x would leave me with an x on its own, make x a subject. So to be able to do this, any equation needs to be solved or rearranged, sorry, so that it makes x the subject. So you've got one x on its own on one side and everything else on the other side. And the reason for that is because we are going to be comparing it to the graph of y equals x. So it comes back to the idea of simultaneous equations and points of intersection. So what I will be doing with these is I'll be looking at this graph of square root of 5 minus x over 2 and the graph of y equals x and comparing those two things together. So that's what's happening here. The exam question will guide you to this, and it will also tell you which one of these you would be using. So you wouldn't be asked to come up with them all in the way that I have just done here. But we've done this just to try and show you that it's just there's a lot of different ways that an equation can be rearranged. Some of them will work and some of them won't, and that's what we're going to be having a look at next. So that's part A done. Part B I'm going to do in the same place, because all you've got to do to turn it into an iterative formula is the x on its own gets an n plus 1 and the x in the function gets an n. So that one's an n plus 1, that one gets an n. That one gets an n plus 1, that one gets an n, that one gets an n plus 1, and that one gets an n. So they are now all iterative formulas that came from this original formula here. I'm not using that one because that was just a little bit of working out to make x a subject. So what we're going to do is choose a suitable starting point and use iteration to find the root. Now, because this is the same as this function up here, I'm going to choose one of the values within my interval, and because we've decided that it's equal to 1.4 to 1 decimal place, I think that's a good place to start. So part C, we're going to do 2 of these. So I'm going to let my starting point be 1.4, and I'm going to look at, for this one, we'll do number 1. So we'll look at x of n plus 1 equals 5 minus 2x squared of n. Okay, so what that means is when n is equal to 0, that will be equal to 1. So to get x1, all you're doing is doing 5 minus 2 times 1.4 squared. This is iteration, so when you get the value for that, to get x2, what you do is you substitute that number into here and you recalculate it. So that calculates to be 1.08. So my next one is 5 minus 2 times 1.08 squared. And that is going to give me 2.667. Faffy, takes quite a bit of time. the calculator can do this for us. So I'm going to go back to the beginning of this example and we're going to generate this sequence using the calculator. So your starting point on your calculator is to put 1.4, so you put your x0 in and press equals. What that does is that answer button remembers the last thing you've put in. So it's remembered that we've put 1.4 in. So I'm now going to type g of x, so this right hand side. So I've got 5 minus 2 times the answer squared. So when I use the answer button, what I'm telling the calculator is, whatever my last answer is, I want you to use that in this calculation. Because I've told it already that I press 1.4 equals first, I've told it that my last answer was 1.4, it will then give me this 1.08. When I press equals again, it already has answer there. So when I press equals, it uses 1.08 because the answer is picking up whatever you used on the last equals. So that's where this one has come from. So to get x3, all I need to do is press equals. So rather than having to keep typing it in, it's just a little bit faster. To get x4, we press equals. Now, what I'm looking for is the root of my equation. And we know from our previous work on this equation that our answer should be close to 1.4 because 1.4 is correct to 1 decimal place. But you can see that this is not working. And if we keep pressing equals, minus 7.1 times 10 to the 19. So this is diverging. So that means that it's heading away from the point that we are looking for. So we've got something that is diverging. What I want to do is kind of link the graphs into this now. So if we have a look at the graph, so this is 5 minus 2x squared. You don't need to worry about all of that stuff, but this is what is happening with this graph. So you've got 5 minus 2x squared is the blue. This line is just the line y equals x. That is the value 1.4 there. So we substitute 1.4 in to 5 minus 2x squared. It gave us 1.08. And what we did is we let that, because that's what y is equal to there, so that coordinate there should be 1.4, 1.08. And then what we do is we let that equal our next x value. So the line y equals x is where you are letting y equals x. So we're letting it go to 1.08. So that's the swap over point. So what you do at that point is you substitute 1.08 into 5 minus 2x squared. And when we substituted that in, it gave us this point here, which is 2.667. That's the y value. So remember, a horizontal line is a y value, a vertical line is an x value in terms of the graphs. So when we substitute that back in, so we've got 2.667, we substitute that back in to be x, so at that point y and x are equal. And so if you do the vertical line to find your next coordinate, it is all the way down here, which was minus 9.228. We then let that equal x, so we let that come across to this line, and then we have to find the graph. Now, because of the steepness of the graph, it's a long way down, so I've had to zoom out quite a long way here. So we've got down to that point there. So that's where we're letting x be minus 9.22. We substituted it in. We got y was minus 165.3. We let x equal that, and then it's going to find the next one. If you look at your diagrams in your notes, it's this one. So this is diverging, and it is a staircase. It started off looking like it would be cobweb, but it's a staircase. And what that means is you start off with your value, you substitute it into the equation, then you let it equal, you let the y value equal x, so we come across there and substitute that in. We let the y value equal x, we substitute it in. Here's the root. So the root is the point where those two cross, because from simultaneous equations, if you separated those two, you will get your two equations, y equals x and y equals, in our case, 5 minus 2x squared. And so what it's doing is it's stepping away from the route that we're looking for, and it won't come back to it because of the steepness of the graph. The next value is a long way down. It's quite a large negative in terms of size, so we'd have to go quite a long way down there in order to work that one out. So that's called diverging, and it is a staircase because it's stepping away. Let's have a look at another one of these. So we're going to have a look at this one. So we'll have a look at 5 over 2x to the n plus 1. So we're going to use the same starting point. So my iterative equation is that. And I'm going to use x0 is equal to 1.4. So if we clear the calculator, oops. So 1.4 is my starting point, press equals, that's put it in the answer. I want to use 5 over 2 times the answer plus 1 equals, so my next value is, so you're just generating your sequence, so x1 is equal to 1.3158, press equals, x2 is equal to 1.3768, press equals, x3 is equal to 1.33204. You will be told in an exam question what accuracy to give and how many of these to do generally if you were asked to generate the sequence. And we can keep going. So you can see this one is converging. And it's settled down now, so 1.35 is looking like the solution to 2 decimal places. We had 1.4 earlier. We've got 1.3508 quite comfortably there just by pressing equals. You can kind of almost see it settling down. So if we look at this one on the graph, so I want to change my function to be I'm going to have to zoom in on this one quite a long way. So it's the same process. I'm starting at 1.4. So what is happening here is we are substituting 1.4 in. We got 1.315. So we're going up to there, then you can see, so the green line is y equals x. We substitute it in, let the y value equal the x value and substitute that back in, which gives me my next y value, which was 1.3768. Substituting that in gives me my next y value, which is 1.332, and you can see that this is getting closer, and what it's doing is it's spiraling round. So when we kept pressing equals on the calculator, once it was settling down on the first few decimal places, it's because it's got really close to this, so it would keep spiraling as it goes. And if we look at our diagrams, that's an example of this one. So it's a converging cobweb. All you've got to do, if you were asked about these graphs, because it is a little bit confusing to look at them this way, is if you just get your head around this process and what you're doing with your calculator, it is the same thing. So you're taking a value, substituting it in, letting it equal your next x value. So that line coming across is, if you think of it as converting y to x, substituting it in, letting it equal the next x value, substituting it in, letting it equal the next x value. If from the diagram you can draw something that's coming inwards, so if we look at the staircase, we're substituting it in, let it equal the next x value, it's getting closer and closer to the root, then you've got something that's converging. If it goes away and you can get a cobweb that spirals outwards, then you've got something that's diverging. So here we had converge, and actually it was a cobweb. And you can see that because it's oscillating if you look at the values from one side to another, so you know that the root is somewhere between these two, because it comes back. If it went 3 1 and then 3 7 and then we went 3 9, etc., you would know that you were staircasing. But because we're going, if we look at this, it's 1 7 3 6, it's jumping from either side of where that root is, so we know that we've got a cobweb. If we wanted to prove that 1.35 is correct to two decimal places, what we'd need to do is almost go back to that idea of trial and improvement. So if we come up with an interval where we know that every value within that interval rounds to 1.35, and then show that we've got a change of sign, we will have proved that we are correct to two decimal places, because if we've got a change of sign, then we must have a root in that interval. So the interval that we're going to use here would be 1.345 and 1.355. That one's not inclusive, but that one would be, because everything in that interval would round to 1.35. Technically, this one is where you've got your 4 9 recurring, but you can't work with that, so we use a 5 at this point. So what you're doing is taking, you've two decimal places there, so you're going one decimal place more, and you're looking at its upper and lower bounds. Okay. When you do this, you need to go back to f of x. So f of x in this case is 2x squared plus x minus 5. So you are doing f of 1.345 and f of 1.355. Okay, so 45 gives me minus 0.037, and that one gives me a positive. So then you would be able to draw the same conclusion as we were drawing in the previous one. So f of x is continuous. We know it is because we have a quadratic, and it's continuous over the interval that we're given. And therefore there is a root. Oops. So the root that what we're trying to prove here is that 1.35, so therefore the root is 1.35 to two decimal places. Slightly different conclusion on the end, helps if I can type. Okay, so just be aware that that's looking for a slightly different conclusion. We are mentioning that it's continuous. We are mentioning that there's a change of sign. This time we're trying to prove that we had that root. So that just finishes off the topic, and that's all there is to it. It's quite a lot of information there. Spend a bit of time on those diagrams, spend a little bit of time substituting the value in and just pressing your equals button, seeing what's happening. You've got 2 more of these that you can try it with, see which ones are working and which ones aren't. From a graph point of view, it's to do with the gradient, and we'll come on to that in one of the later topics. So if you've got a steeper graph, when we were dealing with this, the negative 2x squared is quite a steep graph, and therefore we ended up diverging, whereas 1 over x is a shallower graph at the points that we were looking at. Therefore, we ended up converging. So that's how it's worked out, and you don't need to worry about that. The exam question will work that out for you. So spend a little bit of time on that and see if you can understand how these graphs are working. And I'm going to do this exam question as a separate video.